All right, since our topic is network security, first we have to talk about networks. So we either need to remember them, or if you don't know it, we have to learn it. So we are going to talk about the very basics, the internet, how it works, and so on. So in the past years, I used my own slides, but take pictures from this book, from the slides of this book, because it is a lot easier to explain using pictures. So I was giving reference to this book and the slides. So when I was updating today, I realized that it will be a lot easier to use the slides directly from the book. So it is from the book called Computer Networking, a Top-Down Approach by Jim Kurose and Keith Ross. This is the 8th edition from either 2020 or 2021. So they say a top-down approach because we are going to divide the network into layers. So they are going to start from the top layer, the application layer, and go to the bottom. Actually, this is how we are going to look at it also. But it's a very nice book. I recommend you to read the whole book if you are interested in this topic. So, of course, this is the introduction chapter of the book. So it is to introduce the terminology, and more details will be given later. So the roadmap is as follows. We are going to talk about what is the internet, what is a protocol, network edge, host as access network, physical media, network core, packet circuit switching, internet structure, performance, loss, delay, throughput, protocol layers, service models, security, and also if we have the time, we will talk a little bit about history, or you can simply read the slides. So I always look at the internet in two different ways. One of the infrastructure, where we have all of the hardware which connects all of these devices to each other, and also the software. So this book calls it the nuts and bolts view. Okay. The other view is actually how the end users see it. They don't care about how the hardwares work, what is happening in the background. They see it as a service. So, for instance, you use WhatsApp, you send a message to your friend, and your friend receives it. So, it magically happens. You don't know how it works, but it works. So that is the service way of looking, and this part is actually the hardware and software way of looking. So this book says it is the nuts and bolts. So let's see how they explain it. So there are billions of connected computing devices. We call them hosts and systems. Of course, in the future, we will divide these hosts as clients and servers. But regardless of that, here we are at the edge and systems, as you can see. And the internet somehow connects all of these devices. And nowadays we have many devices, not only desktops or laptops, we have mobile phones, but any smart device actually can connect to the internet. So running network apps at internet edge, so the apps run at these end systems. And the data is transmitted between these devices, so we need packet switches, which forward packets, chunks of data. So in the networking terminology, we call them packets. So these are routers and switches, as you can see here. They do similar stuff, but routers are actually more capable. But of course, these are hardware, so we have to connect these also with each other. So we need some communication links. So this can be either wired connections like fiber, copper, but they can be also wireless like radio or satellite communication. So which we have already talked about in the last week. So when we have lines like this, we are actually connecting it with a physical cable. But for instance, here we have a GSM tower, so it connects to devices in a wireless way. The transmission rate is important. We call it bandwidth. And actually, all of these devices cannot be seen as a single network, but they are actually networks of networks. So internet has to be looked in this way. It is not you shouldn't look at it as a single network, but you should look at it as the network of networks. All right. So this blue represents the network. And of course, each network has different capabilities or consists of different devices. For instance, at your home, you have your computers, mobile phones, but also, for instance, your fridge or air fryer and so on. This is a small network. It connects to the internet via regional internet service providers or local internet service providers. So this way you connect to the whole internet. We will talk about this in the following slides. But another way of looking at it as the service or fun internet connected devices. So there are devices, very different devices like gaming devices, internet phones, fridge, security cameras, and so on and so forth. And more recently, air fryers or everything are connected to the internet somehow. Almost every device have Wi-Fi capability. So you receive some kind of service using these devices. All right, so let's go back to our nuts and bolts view. So as I mentioned, internet is actually a network of networks. So interconnected internet service providers. So the protocols are everywhere. They control sending, receiving of messages. For example, HTTP, streaming video, Skype, TCP, IP, Wi-Fi, 4G or 5G, Ethernet. This is important, and we are talking about this because, as I just showed in the previous picture, we have many different devices. So we should have some kind of protocol so that they can communicate and understand what they are talking to each other. This is why we have many different protocols, and these protocols are determined by standards, and it is generally determined by IETF, Internet Engineering Task Force. And these standards initially started as requests for comments. So this is why it has this name, but every internet standard from them has this abbreviation RFC, then the number like 4,000 something. So currently there are around 10,000 standards, which describes what is HTTP, what is Ethernet, and so on and so forth. So they are very detailed technical documents. So infrastructure that provides services to applications like web streaming. So this is the way how we look if we look at services. So web streaming, video, multimedia, teleconferencing, email, games, e-commerce, social media, interconnected appliances, and so on. Provides programming interface to distributed applications, hooks allowing sending, receiving apps to connect to, use internet transport service, provide service options analogous to postal service. So it is like sending a post through the postal service, but instead we are using hardware, and instead of mail we are sending actually data packets. Okay. So there is an analogy between human protocols and computer protocols, because when you communicate with humans, if there are no problems, you can ask them a question like what is the time, and they can answer it and so on. Or initially you can introduce yourself and so on. So rules for specific messages sent, specific actions taken when message received, or other events. This is what we call a protocol. So in the network protocols, computers or devices rather than humans communicate. All communication activity in internet governed by protocols. Protocols define the formats, order of messages sent and received among network entities, and actions taken on message transmission received. Okay, so here's a very basic analogy between a human protocol and computer network protocol. So human start is as follows. The person says hi. The other person answers as I. So this is the introduction. Alice then asks Bob what time, if he knows the time, and then if he's a nice person, answers the question. Of course, if you know this person, maybe you should. It is of course a cultural thing. First, you have to ask how are you. They will say I'm fine. How are you? And if you're in a very different part in Anatolia, you have to ask again, I'm fine, and then how are you? But this time it is a rhetorical question. You don't wait for an answer. Then you can ask what time it is, and they answer. So this is the same thing with devices. We will talk about TCP connection. So your computer, for instance, wants to visit a web page. So this web page in a server someplace. So you start the TCP connection request, the response to your question. So this is like saying hi to each other. Then you request something, for instance, this web page. So probably there is an HTML file like index.html. So you request it and the server sends this file to you. Of course, maybe in that index.html, there will be some JPEG images. Then you will ask them to retrieve it and so on and so forth. So this is the basic view of what a protocol is. Let's move on to network edge, host access network, and physical media. So let's have a closer look at internet structure. The network edge is actually hosts, as I mentioned. These are at the edge, and hosts can be, classified as clients and servers. By clients, we generally mean ourselves, our laptops, desktops, or mobile phones, because most of the time we are requesting something. For instance, we are trying to visit a web page, and that web page is actually on a server, and servers are often data centers. We request it with these connections, and they answer us back. So this is actually somewhat important because people who see internet as a service generally don't know this. For instance, here is your mobile phone, and assume that there is another mobile phone, your friend here. So when you send a WhatsApp message, people think that this is actually, since both of the devices are connected to the internet, there is a link between them. So they think that their message travels from here to here. But actually what happens is that you send your message to WhatsApp servers, and WhatsApp actually sends it to that person. So this is somewhat important because, this is something very basic, but this actually allows you to understand how it works. And it is also important to know how things work, because if you don't know this kind of basic stuff, anything that comes after that will be magical to you, so you wouldn't understand anything. This is why actually people are, scared of ChatGPT, because they think that, movies like Terminator or Matrix will be real, and, machines will conquer the world. But of course, if they knew how that algorithms work, they wouldn't be worried about that. Okay, so we talk about network edge as the devices. Now let's talk about access networks, physical media. So here we have wired or wireless communication links, as you can see, between these devices, these routers, and so on. At the network core, we have interconnected routers. Actually, these are actually, this core actually connects, countries or continents to each other. This is how we can communicate with the whole world, because otherwise you can, stay in your local area. So how to connect end systems to edge router? Residential access nets, institutional access networks like schools, company, mobile access network, Wi-Fi, 4G or 5G, and so on. So these are very different versions. For instance, in our university, we have institutional access network. So our university provides the internet service, but it can be completely different. So let's look at the cable-based access. So for instance, assume this is your home. You have your devices here. They are connected to a cable modem. So there's a splitter here. If this is via phone line, the splitter divides the data between the phone communication and data transmission. Or you can, if you have more devices, in this example, this is cable modem. So the splitter actually, allows you to connect more devices. But this is coming from the cable head end, right? So there is a cable here. It can be coaxial cable, like we mentioned last week, or fiber optics and so on. But this cable is used by many other, apartments, buildings in your street. So all of you have a single cable coming out of your home, but that is connected to a larger cable here. So that cable actually carries all of these people's communication. So we have to have a way to carry data on a single cable, but carry the data of more than one people. So there are some methods of doing this. One of them is frequency division multiplexing. So different channels transmitted in different frequency bands. So you divide this into channels. For instance, if there are like 9 channels, as in here, 9 people's data will be, divided in this kind of a frequency. Okay. So data TV transmitted at different frequencies over shared cable distribution network. So this cable modem actually is connected to internet service provider, and this is how you connect to the internet, the whole world. So sometimes, there's a hybrid fiber coax. This means that your data is coming as a fiber optics, but then inside the building, maybe it is more traditional like Ethernet cables, like this twisted pair cables that we talked about last time. So this kind of connection is asymmetric because your download speed is higher, between 40 megabits to 1.2 gigabits per second, but your upload rate generally is less, like between 30 to 100 megabits per second. Yes, so network of cable, fiber attaches homes to ISP router. Homes share access network to cable head. That's what I try to explain here. So if you use DSL, the previous one was cable modem. Here it is DSL, so digital subscriber line. Here we are using phone lines, telephone lines. So now your telephone lines enters your building, but this time splitter divided between the phone communication and data transmission. So this time it is connected to a DSL modem. So it uses existing telephone line to central office, DSL AM. So this is DSL access multiplexer. So all of the homes use again the same cable here. This time this central office sends this to internet service provider. So as I mentioned, data over the cell phone line goes to internet. This one by the splitter. Voice over the cell phone lines goes to the telephone net from here. So this is the telephone network. This is the ISP. Good thing about the cable modem is that if you already have cable TV, then you don't have to have a phone subscription, right? But in the DSL you need that. So download speed actually changes due to infrastructure and technology. The download speed can change between 24 to 52 megabits per second, and upload can be between 3.5 to 16 megabits per second. But of course, as I mentioned, this infrastructures always change. For instance, currently, instead of using this, they use fiber optics also until the building and so on. So this might allow higher speeds. So let's talk about access networks, home networks. So in your home, there are many devices connected to router and modem, and it sends this data to central office. Yes, currently at homes, we generally use twisted pairs, which generally provides up to 1 gigabit per second transmission, depending on of course, your cable. If it is very old, like Cat4 or something, you cannot reach these speeds, but it is Cat5 or Cat6, you can reach 1 gigabits per second. With Cat6, you can even reach to 10 gigabits per second, and so on. Wi-Fi access also depends on your modem. If it has, more antennas, you can exceed 54 megabits per second, because with more antennas, you kind of eliminate the noise that causes errors. Yes, so a modem, router, Wi-Fi access generally are sold as a single box. And this is actually what you have at your home most of the time. All right, so shared wireless access network connects end systems to router by a base station, also known as access points. Wireless local area networks, typically within or around building, 100 feet, let's say. So it actually depends the standard you are using, and also the Also, it depends if it is 2.4 gigahertz or 5 gigahertz. So most of the new modems or Wi-Fi's allows you to choose between 5 gigahertz or 2.4 gigahertz. So if you want low latency, 5 gigahertz is for you, which is good for, streaming full HD videos or gaming and so on. But this actually reduces the distance you can send data, because if you use 5 gigahertz, then you cannot go further than 10 meters or something. But with the 2.4 gigahertz, you can even be maybe 100 meters away from the Wi-Fi, but you still have reception. Okay. In the case of cellular access network, so here at the Wi-Fi level, we don't need, permission to use this communication channel. Okay, everybody can buy a Wi-Fi, or all of our mobile phones, etc., use this channel because the distance is not that far. But for the cellular networks, you have to agree with the company and the government, and be a GSM operator and so on. So this is wide area cellular access networks provided by mobile cellular network operators, can be tens of kilometers. So it says that here the speed's 10 megabits per second, but it depends on if you are using 4G, 4.5G, or 5G, and so on. So with this new technology, the speed increases. But of course, if the signals becomes harder to send with these high speeds, because with 5G or 6G, the buildings or the physical obstacles might reduce your transmission rate. Anyway, let's talk about enterprise networks. These are companies, universities, mix of wired and wireless link technologies connecting a mix of switches and routers. So Ethernet is wired access. Older ones are 100 megabits per second. Of course, if you're using a new system, it should be at least 1 gigabit per second. Again, with Cat6, we can have 10 gigabits per second. So in our university, most of the places we have 1 gigabit per second, but in some places we have 100. Currently, I haven't seen 10 gigabits per second, but maybe in some buildings we have. So at the Wi-Fi level, it depends on your wireless access points, capacity of it. So generally, I observe 54 megabits per second, but it can be a lot higher. So this, you can think as this the picture for our university. So at the data centers, we need higher speed, so high bandwidth links between tens to 100 gigabits, which connect hundreds to thousands of servers together and to internet. So here's a picture. Of course, here for between these servers to have higher speeds, instead of classic Ethernet cables, those twisted pair cables, we have InfiniBand and so on. So host sends packets of data. Host sending function is as follows: takes application message. Here we are the host. In this picture, we have 2 packets, and all of these packets are L bits each. And the link between you and the router has a link transmission rate R, say. So what we do is as follows: host breaks into smaller chunks, known as packets of length L, transmits packets into access network at transmission rate of R. Link transmission rate, also known as link capacity, also known as link bandwidth. So the formula is simple. Packet transmission delay is time needed to transmit L bit packet into link, which is L divided by R bits. Because if R is large, then sending L bit is just instantly. But if it's L is larger than your capacity here, you have to divide L by R to see how many seconds you are going to wait. Okay. So let's talk about links, the physical media. Bit propagates between transmitter and receiver pairs. Physical link, what lies between transmitter and receiver. Guided media, Signals propagate in solid media, copper, fiber, coax. We call it we call it guided because we connect two devices with a cable. So since that cable is a physical access, we know where the data is going to. So it is a guided media. But if you send a signal wirelessly, you're actually sending that signal in an area with some radius around you. So it is unguided, like radio, Wi-Fi, GSM, satellite communications are unguided most of the time. So for the guided media, the most popular one is twisted pair, and currently it still dominates. With the category 5, Cat5, you can have 100 megabits per second. With Cat5e, you can reach 1 gigabits per second. Category 6 allows you to reach up to 10 gigabits per second Ethernet. So these are two insulated copper wires. Coaxial cable looks like this. Two concentric copper conductors, bidirectional, broadband, multiple frequency channels on cable, around 100 of megabits per second per channel. Fiber optic cable, glass fiber carrying light pulses, each pulse a bit. High-speed operation, high-speed point-to-point transmission between tens or hundreds of gigabits per second. Low error rate, repeater space far apart, immune to electromagnetic noise. So these are the good things. Here by repeater we mean as follows: you are sending a light pulse for tens of kilometers away. So it is not possible for that light to travel without an error. So between some a few kilometers, maybe 10 kilometers, you have repeaters where the repeater receives the light pulse, which is a bit, and repeats it. So it's actually strengthens the signal. But as I mentioned before, this is a good place to tap into the communication and listen to it. And this is as far as we know how agencies listen to whole internet communications. Snowden documents actually revealed this. So these are good places to actually listen to communications. Wireless radio, signal carried in various bands in electromagnetic spectrum, no physical wire. It is broadcast, half-duplex, sender to receiver. Propagation, environment effects, reflection, obstruction by objects, interference, and noise. So this is why we have to, error correction codes and so on to, prevent errors. We have many radio link types. Wi-Fi, the well-known ones. All of us use this. It can be up to 100 of megabits per second, and the distance is tens of meters. Again, depends on the frequency you're using. For the wide area, we have 4G, 5G, cellular. With the 4G, we have tens of megabits per second, and you have this over 10 kilometers. Bluetooth, cable replacement, short distances, limited range. These are very popular these days because due to smartwatches and smart devices and so on. In an open area, actually, Bluetooth with the current version, you can even send maybe up to 100 meters. But in a building, due to walls and so on, I think the distance becomes 5 to 10 meters. But it is really related to the Bluetooth version. If you are using a very old version like 2.0, I think you cannot send more than 4 or 5 meters. Depends on, of course, the hardware, but still, current version is a lot better. Terrestrial microwave, point-to-point, 45 megabits per second for each channel, and satellite up to 100 megabits per second. Starlink does this, but this is what actually predicted, but in real life we observed around 200 megabit per second at Starlink. So it depends on the position of the satellite and so on. So if you have geostationary satellite, recall that Starlink was low Earth orbit satellite, so it was very close to the Earth, like 700 kilometers or so. But geostationary satellites are at the 36,000 kilometers away from the surface of the Earth, so they stay at the same position. But since they're far away, you have this amount of latency. So this is why it is not good for applications that need low latency. So you cannot have a good maybe voice over IP or video conference call using geostationary satellites, but low orbit satellites are very good for this kind of applications. You can even use play a multiplayer video game and won't notice most of the time the latency. All right, so let's stop here and then continue with network core.